In this video, we'll give several examples of a proof by contradiction. But first, let's talk about the method. To prove a statement by contradiction, we negate the statement and show any contradiction. The reason this works is that either a statement must be true or its negation is true. When we show that the negation of a statement leads to a contradiction, that means that the negation is false, and therefore the original statement must be true. Let's talk specifically about how we show proof by contradiction for an implication. Recall that implication again is a statement of the form P implies Q, where P is the premise and Q is the conclusion. The implication is logically equivalent to not P or Q. This can be verified using truth tables. Then we want to negate the original implication, and to do that we will negate the equivalence, and we apply De Morgan's rule to do so. So not P becomes P, the or becomes and then we negate the conclusion and get not Q. So the negation of an implication is P and not Q. Another way to think of this is we accept the premise but negate the conclusion. And then to show that the original statement is true, we have to show any contradiction. And once again, when we show any contradiction, we are showing that the negation is false, and therefore the original statement is true. Let's begin with the example. So we're going to prove by contradiction that n cubed is not in big O of n squared. So this can be written using set notation as well. And first we have to assume the negation. So when we assume the negation, we assume that n cubed is in big O of n squared. Then we can apply the definition of big O. This means there exists positive constants c and n naught such that for any n greater than or equal to n naught, n cubed is greater than 0, but bounded above by a constant times n squared. Okay, let's consider when we divide this entire equation by n squared. We can do so since we know it will be greater than 0. So we are going to get that n has to be less than a constant. Now, sometimes people will stop the proof there because it doesn't seem possible that a constant could ever be bigger than an arbitrarily large n. But that's just our intuition. We haven't completed the proof. We haven't actually shown a contradiction yet. So let us consider a specific value that would show that this inequality cannot be true. So let's let our n star equal the max of n naught plus 1 and the constant plus 1. Why did we choose n star to be this? Because we need a value of n that's greater than n naught, which would also show that the inequality is false. But so now we consider n star. N star is greater than n naught, and n star has to be greater than c, because it's going to be the max of c plus 1 and n naught. When we do so, we have actually created a contradiction because we've just shown we picked an n star greater than our constant. But by the definition of big O, the constant has to be greater than every value of n. So this is our contradiction. And since the negation of the statement led to a contradiction, we can infer that n cubed is not in big O of n squared. Let's consider another example of a proof by contradiction. In this example, we are going to be considering an implication. Our implication is if 15x plus 111y equals 55,057 for real numbers x and y, then either x is not an integer or y is not an integer. So the first thing we have to do is we have to assume the negation, and the negation is going to be p and not q. So let's write that. So we're going to assume that our equation is true, and x is an integer and y is an integer. Okay, so now we can consider what happened. So if we have that this equation is true, we have 15x plus 111y equals 55,057. Now, from the left-hand side, we can factor out a 3. So we're going to get 3 times 5x plus 37y equals 55,057. We can now divide both sides by 3. So we're going to be left with 5x plus 37y equals 55,057 divided by 3. Now, the left-hand side is an integer, but the right-hand side is not an integer because 55,057 is not evenly divisible by 3, and that's our contradiction. So since 5x plus 37y is an integer, since x and y are integers and 5 and 37 are integers and the integers are closed under addition and multiplication, but 55,057 divided by 3 is not an integer. This is a contradiction. And therefore, the original statement is true. Let's look at one more example of proof by contradiction. We will show that the square root of 5 is irrational. To begin the proof, we have to assume the negation of this statement. So we will assume that the square root of 5 is rational. That means there exists some integers p and q such that q is not equal to 0 and p and q share no prime factors, and you may have also heard this expressed as the GCD of p and q is equal to 1, or that P and Q are relatively prime, and such that the square root of 5 is equal to P divided by Q. Now let's see what we can do with this. The first thing we can do is we can square that equation, so we are going to get that 5 is equal to P squared divided by Q squared, which means that P squared is equal to 5Q squared. Okay, now we want to see what we can do with this. So the first inference that we can make is that, well, since we can express P squared as 5 times Q squared, we can infer that 5 divides P squared, because we've just expressed P squared in terms of 5 and another integer, so it's evenly divisible by 5. Now we want to think what more we can get from this. So if 5 divides P squared, that means 5 divides P, or 5 divides P. So that would also imply, the second implication we can make is that 5 divides P as a prime factor of P. Okay. Now, since 5 divides P, we can express 5P as 5 times some other integer. Okay, now we can go back to our equation that had 5 is equal to P squared divided by Q squared, which is 5Q squared equals P squared. And we can just do a substitution. So this is going to imply that 5Q squared is going to equal 25C squared. Once we simplify this, we get that Q squared is equal to 5C squared. Now, the inference that we can make from this is, first of all, we just express Q squared as 5 times another integer, which is C squared, so we can infer that 5 divides Q squared. So since 5 is a prime factor of Q squared, we can then infer that 5 divides Q, or 5 divides Q, which just implies that 5 divides Q. But now we have a contradiction. We have that 5 divides P and 5 divides Q, but that is a contradiction. Since P, Q share no prime factors. Therefore, the negation is false, and the square root of 5 is irrational.